All right. So I was talking to Mrs. Apples and I said, "Hey, what letters do you guys use for those transformations?" And she was like, "Yeah, we don't really teach it that way anymore." And I was like, "Oh, really?" She said, "Yeah." So I thought it might be a good idea, maybe if you guys had not seen it this way, just to see the notation that I like to use, just all in one location for all of the transformations, because I will use this notation because that's just what I'm used to using for any transformation. Okay, so we've got uh, a horizontal shift. Okay, I use this notation. F of x is going to turn into f of x minus h, right? Where h is my movement left or right, right? What does that mean also? Remember that the change the input value means I change what's going into the function, okay? A vertical shift is going to take f of x and it's going to turn it into f of x plus, now we used plus c. Sometimes it's plus k, depending on whether you're working with like a quadratic. I know sometimes we see it like x minus h squared plus k. I'll say f of x. Sometimes I use k, sometimes I use c. Let's use c, because that's what the book uses more often. Now, those are the shifts. Remember, shifts are pluses or minuses. Horizontal is inside, vertical is outside. Okay? And then we have the reflection over the y-axis. Now, for the reflection over the y-axis, that means I change the x value. It's always the opposite. F of x is going to map to f of negative x. It's going to turn into f of negative x. That means I go inside the function, I put in negative x instead of x. Reflection over the x-axis is going to take f of x, it's going to change the y value, negative f of x. It's going to put a negative on the outside, turn every term negative. Distribute in. If I have the horizontal stretch or compression, I put those as the same rule. You just got to know, if it's a fraction, it's going to be a stretch. If it's a whole number, it's going to be a compression. Remember, those are the opposite ones. F of x is going to turn into f of 1 over bx, right? 1 over bx. That is okay, so if it's a stretch by 2, it's going to turn into 1 over 2x. If it's a compression by 1/2, it's going to be 2x inside there. If it's a stretch by 5, it's going to be a 1/5 x. If it's a compression by 1/3, it's going to be a 3x sitting on the inside. Take the reciprocal of the value. And then the vertical stretch or compression is going to map f of x to a times f of x. A times f of x, where it's just straight up that value, right? Just straight up a times f of x. So if it's like a vertical stretch by a factor of 2, that's 2 times f of x. If it's a vertical compression by a factor of 2/3, it's 2/3 times the entirety of f of x. Now, again, notice the similarities between all of these. All the vertical things are happening outside, right? Here's a vertical, here's a vertical, here's a vertical, right? All the vertical things are happening outside of f of x, happening basically to the entire function. All of the horizontal things are happening within the input. I change the input value, right? Try to keep that in your brain. Horizontal things happen in the inside, vertical things happen to the outside. The shifts are very similar because they're adding and subtracting. The reflections are similar because they got to deal with the negatives, and the stretches and compressions are similar because they deal with the multiplication. Right? So that's kind of like a summary of all the different types of transformations that we can possibly have. Now, what makes them more difficult is the different types of functions that you have to deal with, right? Doing a transformation on a linear function is way easier than doing a transformation on a polynomial, right? Or a rational, or say a trigonometric, right? Which leads us to the next one. Sketch the graphs of the following functions. Y equals 2 sine x. Y equals 2 sine x. Whenever you do a trigonometric, make sure that you're showing one full cycle, right? Go one full, what's that called? Period, right? and then move on. And then put arrows on the end. Okay, sine 2x. First off, what type of transformation is that? What type of transformation is that? Is it happening on the outside of sine or on the inside of sine? Inside. Horizontal something, right? Now, am I adding to x or multiplying to it? Multiplying to it. So I know it's horizontal, stretch, or compression. Which one? Compression, right? Compression, because horizontal things are opposite, they're counterintuitive. So if I see a whole number in there, it's actually going to be like a 1/2 in this case. So this is technically a horizontal compression by 1/2. It's going to take all of the x values and condense them by a factor of 1/2. Okay, now, I always like to draw out original sine whenever I do a transformation. Let's draw out original sine. So original sine goes like this, right? There's original sine. Where was this x-intercept? Where did this used to be before I transform it? Where is that? Isn't that pi? Right? That's pi. Think about sine is y value, right? Look at the unit circle. When does it go back around and hit y equals 0? At pi, at 180, right? Okay, where is this then? Where is, oops, I should move that over here a little bit. There we go. Where is the apex there? Where's the vertex? If this is at pi, what's right in the middle there? Pi over 2. Okay, pi over 2. And this, obviously, of 2 pi over here, and right in the middle, 1.5 pi, right? Halfway between pi and 2 pi, 1.5, or 3 pi over 2. And obviously, we've got +1 and -1. Okay, so that was the original, right? I want to horizontally compress that by a factor of 1/2. Horizontally compress that by a factor of 1/2. So I'm going to go in green, and I'm going to graph this in green. That means horizontal compression means every x value gets multiplied by 1/2. Does anything change with the y values of these coordinates? No. Just the x values are going to change. Like, for example here, does this change my amplitude? No, it still goes -1 to +1. Who's calling? Hi, Mrs. Brown. Yep, he's here. Yep, you're good. Goodbye. Just checking to make sure you made it on time. All right. So horizontal compression by a factor of 1/2. Okay, my full length of my cycle was 2 pi. So what does it turn into now? If it was 2 pi and I multiply by 1/2, what's it turn into? Pi, right? So now here is my endpoint, right? Here is my endpoint. Still goes -1 to +1, though, right? I haven't changed my amplitude. That doesn't change. Don't change my y values. Okay, this vertex, this low point here that was at 3 pi over 2, where does that go? You know, it might be better to do the halfway point. Let's do that first. This halfway point that was at pi, where does that go? Cut it in half. Pi over 2. Right? So now I'm saying, well, this 0, 0 doesn't change. Now it's going to go up, down, up, right? Should be a little less pointy on the bottom. Sorry. Okay, so now this point down here is the one that I was referencing with this 3 pi over 2, right? Okay, if it's horizontally compressed by a factor of 1/2, I'm just multiplying that x value by 1/2. So 3 pi over 2 times 1/2 is 3 pi over 4. So 3 pi over 4. I'm going to tuck that in there. 3 pi over 4. And this pi over 2, which was the apex, the vertex here, now is here. Okay, so that is now, it was pi over 2, so now what does it turn into? Pi over 4. Does that make sense? Whenever I ask you to graph sine, cosine, please make sure that you include where the intercepts are and where each vertex is. Okay, the high point and the low point. I should see the 1, 2, 3, 4, 5, the 5-point summary. Where it starts, high point, where it crosses the x-axis, low point, and then again here at the end. We will actually call this, that middle point, the point of inflection as we get later on. Right? That is called the point of inflection, where it turns from a curve downward to a curve upward, where it starts that change, the inflection point. All right, let's do that again. 1 minus sine x. 1 minus sine x. I should really get my notes, so I'll screw things up here. I'll do a cold turkey. 1 minus sine x. Okay, again, my original, right? My original is just sine x. We kind of went through that already. You know, let me put it in blue, just like the axes. Here, right? Where this is pi, this is 0, this is 2 pi, this was 3 pi over 2, and this is pi over 2. Okay. First things first, let's describe the transformations. It might be better to rewrite it. Negative sine x plus 1. I might think of it better that way. What are the two? I see two transformations happening. What are they? Reflect over x and up 1. Right? Reflect over x, then up 1. Now, people always say, well, what comes first? Is it the reflect over the x or is it the up 1? Because that changes things. Yes, that does change things. Here's what I would say. Go with order of operations. If you plug a number into sine, what would happen first? Would you take the negative or would you add 1? You would take the negative, right? So that's what should come first. Run a number through, and whatever is going to act on it first is going to be the first transformation that you should do. So the first thing I'm going to do is reflect over the x-axis. Reflect over x. And then I'm going to move it up 1. And I have a feeling I am going to run out of room because I did not take into account the up 1. Ooh, look at that. That was almost perfect. Move this little black line out of the way too. All right. Reflect over x and go up 1. Okay, so this 0.00, I reflected over the x value and it stays 0, 0. I think I do have to extend this up a little bit. Yeah, because it was at 1 and negative 1, right? That should be a little lower. 0, 0. I reflected over the x-axis. It does nothing. And then I push it up 1 unit. So it starts here, right? This point here, pi over 2 comma 1, right? This point here at pi over 2 comma 1. I reflected over the x-axis. Where does it go? Pi over 2 comma negative 1, right? And then I go up 1. So it goes pi over 2, 0. This point here, pi comma 0. I reflected over the x-axis. It doesn't move. And then I go up 1. This point here, 3 pi over 2 comma negative 1. I reflected over the axis. It goes 3 pi over 2 comma positive 1. And then I go up 1. So now I have to kind of go here and say, well, that's 3 pi over 2 comma 2. Pi over 2 comma 0. I reflected over the x-axis. It doesn't move. I go up 1. Bingo. So now I go. Sound effects help you draw. Questions about that? Cool. Let me take a look here. What do we got here? Oh, yeah. You know how I talked about how absolute value is going to kind of play by its own rules a little bit? The same thing is kind of true for transformations. Absolute value is its own weird thing, right? Because it doesn't follow a lot of the same rules that we will use for other functions, other families of functions. It's its own thing. Another transformation of some interest is taking the absolute value of a function. If y is equal to the absolute value of x, then according to the definition of the absolute value, then y is equal to f of x when all the y values are greater than 0, and it's equal to negative f of x when all the values were below the y-axis, when f of x was less than 0. So basically, the transformation of taking the absolute value just takes everything below the y-axis, everything that would normally come out negative, and flip it above. Okay? Oh, I'm sorry. I'm saying y-axis. X-axis, excuse me. Everything that would normally end up below the x-axis, normally come out negative, would flip upward and turn positive. So, for example, absolute value of x squared minus 1. Absolute value of x squared minus 1. If I look at the original function inside there, well, that's a parabola. What's the transformation on the parabola? What's that minus 1 telling you to do? Down 1, right? Down 1. It's our parent just flipped, or just not flipped, sorry, just pushed down 1. There is x squared minus 1. Okay, what if I take the absolute value of that? What if I take the absolute value of that? Well, it's going to say that anything that would come out negative in terms of the y values would flip positive. What happens to the things that come out positive? Nothing. They stay positive, right? So what you're going to do is say, well, anything that's normally above the y-axis, I said it again, normally above the x-axis stays above the x-axis. Nothing changes with this stuff. But everything that would normally come out below the x-axis flips positive and acts the exact same way, but just in a positive manner. So this 0, negative 1 would actually turn out 0, positive 1. And isn't this a curved shape? Right? That's what it would look like in red. Okay, that bottom blue part flips upward. Anything that would come out below the x-axis flips upward. It acts the same way. Yeah, you're going to have like pointy ends here. Yeah, and that's going to come out weird for us when we start talking about derivatives. Anything that has a point to it acts really weird. Okay, so it's important to say that, yeah, that doesn't curve there. It's not a curve. It comes to a nice, clean point. All right. Now we have combinations of functions. This composition, right? Composition. And addition and subtraction. You know, when two functions, f and g, can be combined to form new functions when you add, subtract, multiply, and divide them in a manner similar how we add and subtract polynomials and real numbers and whatever. Here's what I want to say about it. I'm going to be asking about the domains and the ranges a lot. The domains and the ranges of any two functions added, subtracted, or multiplied together just is a combination of those two domains and two ranges. Okay, whatever we add, if it was greater than or equal to 0 for one of the functions, but all real numbers for the other, well, the combination is greater than or equal to 0, right? You just got to put them together. If I have all numbers not except for 1, all numbers except for 2, with these two different functions, well, the combination of them would be all numbers except for 1 and 2. Make sense? Okay, it's and in terms of the domains. The only caveat to that is saying that, well, if you have a division of them, you just got to take into account when g of x is equal to 0. You just can't have that either. Okay. When we talk about composition, okay, when we talk about composition, and this is when we have that f of g and g of f, right? The book likes to use this open circle. I don't know. I always had done f of g of x. I mean, I had learned open circle, but I don't know. I don't normally use that. I think it's just easier to write it like that because then you know g is nested inside of f. So f of g of x is just saying you put g as the input of f. You take g of x, that full function, and put it inside f. And you can do, g of f of x as well. That's, g open circle f of x. I just feel like that's a lot of parentheses. G of f of x. So this is saying take f and put it inside g. Now, what's weird about this is that you have to pay very close attention to the domain. You got to pay really close attention to the domain. So here's what you do to figure out the domain. You say, what is the insidemost function? For this one, for this example right here, I would say, okay, what is the domain of G? What are the restrictions on the domain of G? Maybe G can only be positive. Maybe G can't be 1. Maybe G can't be negative. I don't know. What are the restrictions on G? Then you run the composition, look at the very end, and then apply the combination of the two domains, right? So maybe I said, well, x can't be 1 in the domain of G. But then I get to my final, and f of g of x would look like it could be all real numbers. Maybe that x can't equal 1, maybe factored out or something weird or something like that. Well, then the domain still has to include that x is not equal to 1 because it's a combination of the two domains. You look at the insidemost domain, the g of x domain, then apply the ending f of g of x domain to it and combine them. Don't just take the domain of f of g of x. You have to look at the domain of g of x, then apply it to the domain of f. Because if I were to run any number through that composition of functions, it would have to go through g first. So if x couldn't be 1 in g, it can't be 1 in f of g, because I would have to run it through g, then run it through f. That's what a composition is doing, right? It's running it through the insidemost function, taking the output, making the input of the outermost function. Okay, let's do an example to show you. I think the domains come next. That's okay. Let's just do some composition real quick, though. We're going to do f of g, then g of f. F of g, then g of f. Okay, if I've got f of x is equal to x squared, just our parent quadratic, and then g of x is just a linear function, x minus 3. All right, so if I have f of g, and again, I like to write it as f of g, excuse me, f of g of x. So that means I'm going to take g and put it inside f. So f was x squared. So I'm going to take g and put it in f. Follow me there? That's composition. All right, let's reduce it down. That's x minus 3 times x minus 3, or in other words, x squared minus 6x plus 9. That's f of g of x. See what I was talking about with the domain? It's really hard to describe here because it's always all real numbers. Like, I would look at the domain of g. Well, it's linear, so no restrictions. So no restriction on the domain of g. And then I would look at the ending and say, well, that's quadratic. There's no restrictions on the domain of a quadratic either. So the domain of the full composition is all real numbers. Now let's flip it. Let's do g of f of x. Well, that's taking f and putting it inside g. That one's a lot easier. Taking this x squared and putting it into there. Oh, wow. Okay, that's it. Some are a lot easier than others. It depends on what's going in to what. Really depends on the difficulty of the functions. Nothing to simplify there. Sweet. Okay, let's take a look at the next one. Yeah, now we got to find the domains too. Okay. Let's find f of g, g of f, and g of g. Okay. Let's do part A here first. F of g, that means f of g of x. So which is f of, I sometimes write it like this, just to remind myself what's happening. I sometimes put the function g inside the notation of f. Like f of, and I'll put g of x in, radical 2 minus x. So that's telling me take f and put in radical 2 minus x. So f was radical x. So it's going to be radical of radical 2 minus x. And I believe that is the, if a square root of a square root, that's the fourth root. Fourth root of 2 minus x. Yeah, fourth root. Square root of a square root is the fourth root. This would be like taking something to the 1/2 power to the 1/2 power, right? That's a square root taking a 1/2 power. So 1/2 of 1/2, multiply the exponents there, that'd be a fourth, 1/4. So fourth root of x. Fourth root of 2 minus x. So there's f of g. And then I have to say, okay, what's my domain? What's my domain? Well, it's restricted here, right? What is the restriction on the innermost? What is the restriction on g? Well, 2 minus x has to be greater than or equal to 0, right? That's the restriction on g. Okay, well, add the x over to the other side. So x has to be less than or equal to 2. Right? There's the domain of g. X has to be less than or equal to 2. Because if it's greater than 2, what happens? If I plug in 2.1 here, 2 minus 2.1, it's negative 0.1. No good. Non-real. So that's why the domain is less than or equal to 2. Well, okay, now, I then have to take that, I'm not done yet. Then I have to take that domain and apply it to 2 minus x, or fourth root of 2 minus x. Do I have to change it at all? Is there anything else to combine it with? No, because wouldn't I be doing this exact same thing? Right? Inside the radical still has to end up positive, right? And I'm just going to end up doing this exact same thing. So the domain does not get changed at all here. There's nothing to combine it with. There's my domain. I'm going to move this up here for space. All right. Let's take B. G of f. Okay. So that's g of f of x, which is g of, what is f of x? F of x is just radical x. So now radical x goes in to g. So it was 2 minus x, so it's now 2 minus radical x. There's actually nothing we can do to that. There's nothing that we can do to reduce that. The tricky part is the domain. Okay, the domain for this. What's the innermost function? F. What's the restriction on the domain of f? Greater than or equal to 0. Okay, now look at the domain of the final. Now this has some different restrictions. 2 minus radical x has to stay greater than or equal to 0, right? 2 minus x has to be greater than or 2 minus radical x has to be greater than or equal to 0. Okay, well, let's add the radical x over to the other side. Square the opposite side. Okay, so now x has to be less than or equal to 4, but still greater than or equal to 0. Do you see how I have the two different domains? One from the innermost function, one from the final. Combine the two. So my full domain here is 0 to 4. Greater than or equal to 4 yet, greater than or equal to 0 yet still less than or equal to 4. Those are the only possible numbers I could plug in. Questions about that? For the sake of time, I think those are the two most important ones that we will do there. I mean, that shows you an example of the domain getting weird. I think that the other two are just pretty similar. Be careful here. The notation is just saying take F and put it back into F. Like you would say F of, for part C here, you would say F of X, which is F of radical X. So you would just say radical X, fourth root of X. I guess I'm doing that. Okay. Domain is greater than or equal to 0. The innermost was greater than or equal to 0. The final is greater than or equal to 0, and so on. And then for the other one, you do the exact same thing. It would be radical 2 minus X. Just nested in each other. The last thing I want to take a look at is the fact that you can have like triple composition, or maybe even more, right? I could have f of g of h of x. Just 3 functions going on at the same time. That's okay too. You can have 4 if you wanted to. Go crazy. It is possible to take the composition of 3 or more functions. For example, the composition function f of g of h of x is found by first applying h, then g, then f, right? Just kind of nesting them inside one another. H goes in the innermost, then g is the second, then f is the outermost. So we're just going to find f of g of h if, so I'm going to rewrite it here so it looks a little nicer. F of x is x over x plus 1. G is x to the 10th. And h is just a simple linear x plus 3. I'm just going to chain them together. All right, when I do that, if I have f of g of h of x, that's going to take f of g of, what is h? X plus 3. Right? You follow me there? Okay, now what is g of x plus 3? Well, that is f of g of x plus 3 is x plus 3 to the 10th. You follow me there? I take h, I plug it into g, and I'm going to take that and plug it into f. No, I'm not going to force you to reduce the x plus 3 to the 10th. No, thank you. So now this is my input. This full thing is my input. That's what's going to go in for these two x values. Okay? So that means that this final is x plus 3 to the 10th over x plus 3 to the 10th plus 1. That's f of g of h. And you can kind of see them all because we didn't reduce them. I see the innermost function of h as the x plus 3, the second function as the x to the 10th power, the third function as the x over x plus 1. And then the next problem is kind of essentially the exact same thing. Taking it apart now. Can you recognize all different parts? It says f of x is cosine squared of x plus 9. Identify f, g, and h. Let's see if we can identify all 3 parts. Now remember, that notation of cosine squared of x plus 9. Cosine squared. Why is this 2 next to the cosine? Are you essentially squaring? What are you squaring here? Well, remember that this is equivalent to saying cosine of x plus 9 squared, right? That cosine squared of x plus 9 is essentially saying cosine of x plus 9 squared. It's a little bit easier to see what each piece is when I do it that way. What's my innermost function? What's my innermost? X plus 9. That's h. What's my second function? What's my middle? Cosine, right? Cosine of x. And what's my last function? The squared, x squared. You see how that works? And if you were, if you were unsure, like, oh, did I use the right function there? Am I just put it back again? Take x plus 9, put it into cosine. Take cosine of x plus 9, put it into x squared. Cosine x plus 9 quantity squared, which gets us back to cosine squared x plus 9. Okay. All righty, let me stop the video.